In this section now, let's consider the consequences of the Earth's revolution around the Sun once per year. We're going to come back later to the controversy of how we know that it's the Earth moving around the Sun and not the Sun moving around the Earth. So as the Earth moves around the Sun appears to move against the background stars. When the Earth is in this location, and there's some stars here, the Sun appears to be amongst these stars. But as we move around, now the Sun appears to be around these stars. The Sun is not actually moving. It's the Earth moving around the Sun that appears to have the Sun move. So as the Earth moves around the Sun, different constellations are visible at night. The appearance of the sky just after sunset is thus different at different times of the year. Say January 1, when the Sun is in Sagittarius, Gemini will be overhead, whereas March 1st, when the Sun appears to be in Aquarius, Leo will be directly overhead at night. So, as the Earth moves around the Sun appears to trace a path through the sky, and that path that the Sun traces is called the ecliptic. It has nothing to do with ellipses or eclipses, it's just a name. And note that the constellations that the Sun passes in front of are the signs of the zodiac used by astrologers. Now, the direction of the revolution around the Sun is the same as the direction of rotation around the Earth, ignoring the 23.5 degree tilt for now. So if you look down from above the North Pole, the revolution and rotation of the Earth are both counterclockwise. And later on in the course, we're going to find that many other bodies in the solar system show the same sense of revolution and rotation. And this rotation is a clue of how the solar system is formed. Now, there's a number of important effects that are caused by the fact that the Earth's rotational axis is tilted with respect to its orbit around the Sun. So the Earth is tilted slightly on its axis as it orbits the Sun, and the tilt is 23.5 degrees. So, at this time of year, when the northern hemisphere tilts towards the Sun, and the southern hemisphere tilts away, you notice there's this place, even as the Earth rotates, it's never going to get the Sun, and a place that's always going to get the Sun. The northern hemisphere gets more sunlight. Whereas over here, when the northern hemisphere is tilted away, the northern hemisphere is going to get less sunlight. The value of this tilt was set at the time of the formation of the Earth. The Earth's axis points in the same direction throughout the year. It points towards Polaris. So as it goes around, sometimes it'll be pointing towards, sometimes pointing away from the Sun. And that means we're going to get more or less sun in different latitudes, and we get our seasons. So the Sun's position on the sky changes from north to south of the celestial equator and back as we go through the year. The Sun is actually on the celestial equator September 21st, the autumnal equinox, where we have equal day and equal nights. The Sun gets furthest south on December 21st, or the winter solstice, where the Sun appears to stand still. And then it gets back to the celestial equator on March 21st, the spring equinox, and it gets furthest north on June 21st, the summer solstice. So, a side note, the seasons are reversed then in the southern hemisphere. And once again, this is due to the tilt of the Earth's axis. So, do Australians dream of a white Christmas? Probably not. It's midsummer. So, what happens is the Sun is higher in the sky in the summer as it moves north of the celestial equator. That means the ground gets hotter. If you're near the equator, the Sun will pass to your south in December and to your north in June. If you're on the Tropic of Cancer at 23.5 degrees, the Sun will always pass to your south at noon. And we can see then why we have seasons if we look at the Sun in the summer and winter. So this top picture is what it would look like in the summer. So this is the celestial equator. It starts due east. The Sun in summer actually rises a little north of east. And as it traces this path in the sky, it's always north of the celestial equator and sets north of west. So the path that it takes is very long. You get a lot of sun. Whereas in the winter, when the sun is south of the celestial equator, the sun will rise south of east and come and follow this path and set south of west, and it's not in the sky as long, and so I get less energy from it. It's cooler. On the equinoxes, the sun rises and sets with on the celestial equator. So as we move from summer to winter in the northern hemisphere, the positions of sunrise and sunset move southward. It's really easy to monitor this. Above the Arctic Circle, the sun becomes circumpolar in the summer, so that the sun does not set below the horizon, and in the winter it doesn't rise above the horizon. Now, the elliptical orbit of the Earth causes it to be a bit nearer to the sun in December rather than June. This effect on our climate is much less than the tilt of the Earth's axis. So we're actually closer to the sun in the northern winter than we are in the northern summer. The Earth is actually pretty circular. This elliptical orbit is really deceptive. It's almost perfectly circular. It's just slightly elliptical, and we'll come back to that later.